You're probably pretty much in the B range, and if you're above that, well, that's very good. You're doing very well. All right, experiment 5. This is a picture from a spectroscope like you use. And again, you have wavelength down here, 4, 5, 6, 700, whatever. This is a spectroscope pointed at a GE fluorescent light. This was the practice exercise that you did, pointed at the lights in the room. And again, you get bands corresponding to various emissions. In the report, I'm asking you to give me the brightest band at the highest wavelength. And what you want to do is give me this number. So about 620 here would do. Okay? Get my little toy. There it goes. All right. Why does this happen? Well, recall that this is an atom. Nucleus is in here somewhere, a little tiny thingy. And these shaded areas represent the different quantum levels. Remember, they also correspond to the period numbers on the periodic table. So here we have different energy levels. And let's pretend that we have an electron in the innermost shell here. So it would be an S. We take and we pump energy into this atom. What happens is this electron will absorb that energy. Come on. There it goes. It absorbs the energy and is promoted to one of the higher level energy orbitals. Okay? So it absorbs the energy and it bounces up. We use a little asterisk to indicate an excited state. So this electron is very excited. It, lives down here. Finally, it's way up top. Look around, see what's going on. It's neat. But it's not real happy up here. So what happens is it's going to drop back down to where it came from. And when it does, it emits that energy. And it emits it as light. Now, this distance that it drops is set by the different quantum levels. So it's a discrete amount of energy. That means that this photon that comes off has a particular wavelength. Wavelength is associated with its energy. When you look at this in a spectroscope, we see the nice line corresponding to this one wavelength. There are lots of different orbitals it can go up and down to, or energy levels, quantum levels. So you can get multiple lines. Again, what I'm asking for in the lab report is the highest energy, the brightest line with the biggest number. So make sure you know that. Every element has a unique electronic structure, and so the spectrum is unique for every atom. It's a very, very nice way to identify what atoms are in a substance. Now, what we did for the flame test was a very, very crude version, a very classic version, I suppose. Taking the wire, dipping it in, sticking it to flame, and we see a color, right? That's what we did. There's a much more interesting, much more exciting way to do this. What you do is you take a bunch of little watch glasses and line them up, and you put all of your metal salts in each of them. You put a little bit of alcohol in each of them, and put one down here with just alcohol and light it on fire. All right, turn off all the lights, stand back, take another little beaker of alcohol, do like this, so the flame just goes whoosh everywhere. Let's look at that. So that's what happens when you throw your flame in.
Very dramatic version of the flame test demonstration here. First we have alcohol burning blue, then we have some barium chloride with barium ions burning a yellow, a dirty yellow color. Then we have boron being green, strontium giving us the crimson red color. Next is calcium giving us the orange. Not showing up very well here in the next one, but the red tints inside of that orange there's some impurities there. That is lithium. Next we have sodium giving us a characteristic yellow flame. Then we have copper with its green color. And finally potassium with the purple or lilac shade.
So that's the fun where you do them all at once, but you need a very dark room. And I don't know, Triton probably wouldn't like it if we threw flaming alcohol all over the tabletop, but it's much more fun. Any questions about what we did? Make sure you understand the basic nomenclature. Make sure you understand essentially what's going on. And you need the highest wavelength numbers for the two gas discharge lights. Okay? Any questions? All right. First in this chapter, we talk about aqueous solutions. And we'll review states and stuff like that. And then we're going to do the gas laws. Now, the gas laws are a little complicated, but you will actually be tested on these on a fairly simple mathematical basis and on an intuitive basis. Okay? So when you see some of these problems and everything, don't panic. It will be appropriate. This is water. We'll talk about water in just a moment. The little numbers here on the atoms, 2.1, 3.5, these represent the electronegativities of the atoms in water, the hydrogen and the oxygen. Now we talked about electronegativities. We basically said that this is the affinity that an atom has for its electrons. If you have a high electronegativity, it really likes to hang on to them tightly. If it's a low electronegativity, they're really loose, they'll let them go. The electronegativity kind of follows a ramp in the periodic table. Down in this quarter, for francium is 0.7, and all the way up here with fluorine is essentially 4. So it kind of ramps up this way from one end to the other. When you have a covalent bond between atoms of different electronegativities, we said that the covalent bond would be polar. So this is hydrogen fluoride, HF. Fluorine, electronegativity of 4, hydrogen, 2.1. If you look at the electrostatic potential map, now remember blue is electron deficient, red is electron rich. What happens is fluorine is sucking all these electrons down towards itself, leaving the hydrogen electron deficient. That's simply due to the electronegativity. Now, we can show this using what's known as a dipole, and it just looks like this. It's an arrow with a cross at one end. This is the positive end, and this is the negative end. We say this molecule has a dipole moment, okay? Just a word. Well, we're talking about water, so let's start off by just dealing with water itself. For an exercise here, go ahead and draw the Lewis structure for water. Okay? Oxygen is group 6, so you want 6 electrons around it. Hydrogen is group 1. We have 2 of them. We're going to place those around the oxygen. Here's our oxygen. We have 6 electrons, 2 pairs, and 2 singles. We have 2 hydrogens. They have 1 electron each. We'll put them like this. And now it's very, very clear that we can make covalent bonds this way and this way. So we'll just draw these as dashes. All right, so this is water. Now, I've drawn water like this at right angles because that's a good approximation for what water looks like. Remember, we talked about valence shell electron pair repulsion. There are 4 things around this oxygen. So that means the electrons are going to arrange themselves in a tetrahedral manner. That way they're as far apart as they can get. That means that the 2 oxygens, these guys, or 2 hydrogens, must be close to each other on one side. The overall geometry here is referred to as bent. Now that's important. All right, let's do this in terms of electronegativities. Hydrogen we know is 2.1. And oxygen is 3.5. Now those are different numbers, aren't they? That means that this covalent bond and this one are both going to be polarized. Each of these has a dipole. And now if you think about it, what this predicts, because this molecule is bent in this geometry, that this end of the molecule is going to be positive, and this end, where the electrons are being drawn towards, will be negative. So we'll have a molecular dipole that looks like this. Positive on this end of the molecule, negative up here. If we look at the electrostatic potential map, that's what we see. Nice blue end, this is the positive end down here, and the negative end up here by the oxygen. The fact that water is polar like this is the thing that allows it to dissolve ionic salts. That's very important. If water was not bent geometry, if it did not have this dipole, it could not dissolve salts. Let's look at exactly how this happens. This is a little movie. This is supposed to represent a block of sodium chloride. When I push the button, water molecules will come in, and one by one they're going to lift the ions off of this little crystal and take them in solution. So it's a fun movie. Let's watch it. As they come in, you see the water surround the ions, take them off of the crystal face, and take them away. And that's how dissolution of an ionic solid happens in solution. But if you were really paying attention to this movie, you should have noticed that the way that the water takes the various ions off is different for the cation and the anion. When we had the anion, the waters surrounding it were all oriented so that the positive end, that is the hydrogens, were pointing towards the negative source. So it kind of looked like this. Here's our chloride anion, and here's the positive waters around it. The sodium, just the opposite. All the oxygens are pointing in towards the sodium, so the negative charges are pointing in towards the positive ion. This is how water can stabilize ions in solution. Otherwise, there's no way you could rip apart this solid. No way. You've got to be able to take these ions and make them more stable in solution than they were in the crystal. And again, it's done simply because the water is able to wrap itself around the ions and disperse this positive charge. Any questions? All right, let's just do a little bit of nomenclature here. Solubility. When we talk about solubility, we mean that something is dissolved in something else. This is a homogeneous mixture. When we put a number on this, with the term solubility is the maximum amount of a substance that we can dissolve in a given amount of a liquid. For example, if we're at 25 degrees centigrade, 1 atmosphere, magnesium carbonate has a solubility of about ½ a gram per liter. That's how much you can dissolve in 1 liter of water. When you have that amount dissolved, we say that solution is saturated, so it can't get any more. 2 terms to remember. Solvent is the thing doing the dissolving, like that would be water. And the solute is the thing being dissolved, that is, as we saw, sodium chloride. So solvent and solute. Now, solutions here are defined as being saturated if we basically fill them up with as much as we can, right? But actually, you can make a solution that's supersaturated. So in a supersaturated solution, you put in more than you're supposed to be able to. Supersaturated means you have more dissolved than the solution is supposed to be able to hold. Now, a supersaturated solution is very unstable because the stuff wants to come out. This is a really neat little movie. This is a supersaturated solution of ammonium chloride. Ammonium acetate. It's a nice clear solution, just looks like anything else, but you have to be very, very careful with it because otherwise it will start crystallizing. So it's just sitting here on the bench now, and it's happy. What we're going to do is take a teeny tiny crystal of ammonium acetate, just one, going to drop it down the neck of this flask so it hits the surface. Watch what happens. There it goes, it hit. The second it hit, see the crystals form? And very, very quickly, the entire flask now just fills with crystals of the ammonium acetate. Very, very neat demonstration to do. Very difficult though, because if you take this flask, a supersaturated solution, and so much as jiggle it, it won't come out like that. So it's difficult to do. Any questions? So you can have saturated and of course supersaturated, but supersaturated is very unstable. All right, we also talked about the basic rule of thumb for solubility, and that is like dissolves like. Water dissolves things that are polar, because water, as we just saw, is a polar molecule. It has polar covalent bonds. Anything with polar covalent bonds, like an OH group, this is alcohol, ethanol, has an OH, that's a polar bond. It will dissolve in water, and that's what we have here. Oil, which is basically just a hydrocarbon, does not have polar covalent bonds. And because of that, it does not dissolve in water. It is nonpolar. Water dissolves polar things. That's why we have oil and water here, and alcohol and water nice and uniform here. Now there's another concept that I'd like to address, and that is once you get an ionic substance dissolved in water, or a polar substance. It can be of either two forms. We'll call these electrolytes and non-electrolytes. An electrolyte is a solution that will conduct an electric current. Non-electrolyte does not conduct an electric current. Water by itself is a non-electrolyte. Water by itself does not conduct electricity. But if you put a salt in it, like sodium chloride, something that forms ions, then the ions will in fact conduct electricity. I have a demonstration. This is a little device, got a battery and an LED on it, and a couple little probes down here. Very, very simple device. You stick it in a solution. If you can conduct between the two electrodes, then the light lights up. I just happen to have two solutions. This is water, and this is water with some sodium carbonate dissolved in it. So this is deionized water from the lab. And we'll put this thing in there, and by gosh, nothing happens. Everyone see, nothing happens. Now, go over here. This is the sodium carbonate dissolved in water. Stick it in, and if I'm lucky, it works. So the ions in the sodium carbonate are conducting electricity, and the thing lights up. Now, this is a diagram of kind of what we did. We have two probes here, we have a battery of some sort, and we have a light indicator. An electrolyte will conduct the electricity, you get your light. Non-electrolyte does not conduct, and you don't. Now, when I was a child and I went to school, we did this in lab, but we didn't use things like batteries and whatever. We did, well, you plug this sucker into the wall and you used a 100-watt light bulb, okay? And so you had these probes and you had salt water and you had 110 volts, and we simply took these and stuck them in, and by gosh, the light lit up, or it didn't. Very nice. Could you imagine today with the putting a bunch of college freshmen or something in a lab with 110 volts and solutions that conduct electricity? Doesn't work. One other thing to say, as we demonstrated, water itself does not conduct electricity. But that doesn't mean you can take your curling iron in the tub. Okay? Because there's enough salts in the water that's in your tub that it makes it a very good conductor. And that's why you fry. So don't do that. This slide just has bottom line. If you form ions, you're going to be an electrolyte. Again, the ions are all wrapped up in the water. If you don't form ions, but you're a polar compounds, this is sugar, will still dissolve in water. But if they don't form ions, they don't conduct. That's only true for very good deionized water, however. So don't try this at home. Any questions? All right. The fact that water is polar like this also allows it to do something else. Something else is very interesting. And this is hydrogen bonding. If you think about the water molecule, you have positive sections here, and we have a negative section up here. We actually have, because this is tetrahedral, remember, we actually have electrons coming out in two directions up top. If we take this water molecule and we put another one next to it, we form what's known as a hydrogen bond. The hydrogen here is attracted to the negative oxygen, and it forms a bond. Now, it's not a really strong bond. It's about 1/20th of a real covalent bond. But still, it's a bond. Now, if you think about water, we also have a hydrogen on this side. So we could put another one there. And here we have two hydrogen bonds. This is an oxygen up top, isn't it? It can be a hydrogen bond acceptor. So we could put another one up top here. And now if you think about it, we have hydrogens here, we have another oxygen, another hydrogen, more hydrogens. We can just keep doing this forever, can't we? In fact, every water molecule can form at least 4 hydrogen bonds. Water exists as this massive array of hydrogen bonded atoms. This is one of the very unique properties of water. Water is the best molecule we know of for hydrogen bonding. You can actually do a calculation. This is a cluster of water. And this is calculated. All these distances are calculated. And you can see the hydrogen bonding here. Look at these guys. This oxygen has essentially swallowed half of this hydrogen, even more of this one. See these guys? This is how water exists. It's a massive hydrogen bonded complex. Now these hydrogen bonds don't last long. Every 1/1,000,000th of a second, all of these hydrogen bonds rearrange. But they're always there. This is why water is so high boiling. And really, this is why water is essential for life as we know it. There's no other molecule that we know of that can substitute for water for all the things that happen in, well, physical chemistry and in biochemistry. Now, in biochemistry, you've probably heard of hydrogen bonding. These are 2 DNA bases of CT, and they pair up because they can form unique hydrogen bonds with each other. On the top here, we have an NH, and this is an oxygen. So we can form a hydrogen bond this way. Here we have an NH and a nitrogen. Well, this has a lone pair of electrons, so we can form another one. And at the bottom here, we have an NH and another oxygen, so we have a third hydrogen bond. This pattern of hydrogen bonding is what allows the DNA bases to line up properly. This represents a simple thing of DNA. Again, this is what we were looking at. Here's our GC pair. We have hydrogen bond here, one here, one here. This is the other one, is AT, adenine and thymine. Here we only have 2 hydrogen bonds. So if you have an adenine, it cannot bond with a cytosine. And likewise, a guanine cannot bind with a thymine. So this is how the DNA code works. Only one particular sequence can bind to one particular sequence on this side. Very unique. We'll talk a little bit more about biochemistry in a couple chapters and look at a lot of really neat pictures. This is a space-filling model, calculated space-filling model for a DNA helix turn. These are phosphates on the outside, the blue things, and the bases that are hydrogen bonding, these are these guys. And here, and you see that they're stacked up. It's actually interesting because they're stacked up in a column like this. This column of stacked DNA bases actually conducts electricity. Now, nobody really knows if that's used in biology or not yet, but it actually is like a little wire of some sort. Any question? All right, let's go ahead and talk just a little bit more about intermolecular interactions, because these are important then in the gas laws. When we talk about intermolecular interactions, we're talking about the way different atoms or different molecules interact with each other. I'll tell you the bottom line here. The bottom line is that every substance, every molecule, every atom has an inherent attraction for every other one. There are 2 or 3 ways this happens. This represents sodium and chloride ions. And these big balls just represent something benign and nonpolar like argon. Argon's an inert gas. And this represents the electrons around it. If you take something like argon in the presence of ions, what happens is that the electron cloud will actually modify itself. It distributes like this, so that the electrons, in the case of the sodium, will be polarized towards the sodium. Here the chloride electrons are repelled, so that we have a positive region here next to the anion. So the electrons around an atom are very polarizable. And they will do this, and this creates a significant interaction between the molecules and the ions. Now this is very important if you happen to be a fish. Okay? We all know that fish swim in the water and they breathe oxygen, right? Well, oxygen is very nonpolar. Nonpolar. Water is polar. So think of oil and water. They don't mix, right? So how in the world does the oxygen get in the water? Well, it has to do with the induced dipole. This is an oxygen. We're going to sit it next to a water. Now we've looked at this. We know we have a positive end and a negative end for our water. When you do this, when oxygen comes here, what you actually see is polarization of the nonpolar molecule, and it polarizes enough. This bond is strong enough that oxygen dissolves in water. Very important again if you're a fish, and actually nothing would be alive on Earth if this didn't happen. Just plain old billiard balls by themselves. 2 molecules of argon. You would think they would have no affinity for each other at all. But again, when they come close together, the electron clouds polarize such that we wind up with a positive region and a negative region, so they stick together. If you go to organic chemistry, you will talk about van der Waals forces. Van der Waals forces are basically the same as these dispersion forces. It's just the automatic polarization of the molecule, of a nonpolar molecule, when it's sitting next to another. We'll see that these intermolecular forces are what define the concept of state of matter, physical state. And when we talk about gases, the molecules have enough energy that they can totally overcome these weak interactions. So let's go ahead and do this. This is the gas laws. Now the gas laws are going to have a little bit of math involved. But I'll say once again, the questions on the exam will be more intuitive or they'll be very, very simple calculations. Let's go all the way back to chapter 1 or so. We talked about states of matter. We know that a substance, we'll do water here, can exist as a gas, so water vapor up here, as a liquid, and as solid ice. Different states of matter have different physical properties. Solids have defined shapes and defined volumes. They just sit there as a lump. Liquids have a defined volume, but they take on the shape of whatever container you have. And a gas basically will take on the shape and the volume of whatever container you put it into. Well, that's how they differ. Now, all of this happens due to intermolecular forces. These are defined as something called the kinetic molecular theory. And the simplest way to think of the kinetic molecular theory and intermolecular forces is to imagine a lump of magnets. These magnets are all held together by this force, magnetic force, and this would represent a simple solid. These particles are all held together by these intermolecular forces in a lump. Now, the kinetic molecular theory also tells us that nothing ever sits still. If you have children, you know that. So the particles in a solid are moving, but the intermolecular forces are strong enough that they can't get away from each other. So they just sit there and they vibrate. Just sit there in a lump and shake. Now, if we take this and we pump in some energy, enough energy to more or less overcome some of the intermolecular forces, we get a liquid. A liquid, we are slipping and sliding all over each other, but they don't have enough energy to actually break the bonds that are holding the particles together. Finally, if we put in lots of energy, we get to the gaseous state where we have totally broken all of the intermolecular bonds, and these guys are just bouncing and flying all over the place. That's a gas. In this chapter, we're going to talk about gases. So let's very quickly just say what we know about gases. Note that there's lots of space between the particles here, right? They're moving really, really fast, and they don't stick together. That means a gas will have an indefinite shape, and it takes on the shape of its container. That's because it just keeps flying until it hits the wall. It can expand or compress. That's because there's so much space between the particles. You can squeeze them down, and if you put them in a bigger container, they just keep flying further before they hit the walls. Finally, because they're going so fast, they diffuse uniformly. So every sample you take at any point is going to statistically have the same composition. So they have an indefinite shape, you can expand and compress, and they're uniform. Any questions? Now, I said that these little particles are flying around like mad. And as they're flying around, they keep going until they either hit each other or they hit the wall. Okay? This, when it hits the wall, is going to transfer a little bit of its energy to whatever it hits. This little bit of energy results in a pressure. This is called gas pressure. Basically, it happens when molecules or particles hit the wall. This is actually a calculation. It's a movie of the output of a calculation, but each of these little particles represents a gas particle. The walls here are solid, but this barrier up top actually is floating on it. And every time one of these gas particles bumps into it, it pushes it up a little bit. You see it kind of bounces up and down because it's a real-time calculation. This is gas pressure. The pressure from the collisions of the molecules with the barrier exerts a pressure. Now, this pressure is actually quite significant. It really, really is. Pressure of the atmosphere here on Earth, as we're sitting right here, is 14.7 pounds on every square inch. Now, square inch is what, that big? You've got 15 pounds of gas pushing on every square inch. If we didn't have gas inside of us pushing back, it would just squish us down to nothing. The pressure would be phenomenal. Now, when we measure gas pressure, we're going to use what's known as a barometer. Now, there's a variety of types of barometers. This is a classic weather barometer here, measuring atmospheric pressure. Rainstorms and stuff like that tend to have low atmospheric pressure. So down here, it looks like it's going to rain. High pressure is associated with nice, happy, sunny days. So this is a weather barometer. This is a weather barometer with a little strip chart recorder. It's a very antique instrument now. This guy is a laboratory manometer. You hook it in line with a vacuum pump and whatever experiment you're doing. And on this scale here, you can measure the pressure differential. And this one's my favorite. This is a sealed glass globe, air inside, and a blue liquid. This little arm is connected to the blue liquid, goes up top and up like that. I grew up in Florida back in the old days before there were satellites and whatever. And actually, hurricanes in those days could really sneak up on you because there was no way to tell if one was coming unless some ship ran into it or something. So everybody had one of these little suckers. Now the neat thing about this is at normal atmospheric pressure, this thing's at equilibrium. We have air in here, we have liquid, and it just sits there. But if the storm with its very low pressure is coming, then the air here will expand. As it does, it pushes the liquid this way, and it squirts out the top. If it squirts out the top, you know darn well you better get out of there. So that's the old-fashioned type of barometers. The ones we're going to use or talk about in lab are these guys. This is the classic mercury barometer. It consists of a tube filled with mercury. You have a vacuum at the top, and it's stuck down here in a puddle of mercury, a little container of mercury. Air pressure pushes down here with its 14 or 15 pounds per square foot and is balanced by this vacuum at the top here. You measure the height from the surface of the mercury to this meniscus up here. This height represents the pressure in terms of milliliters. As part of lab, back in the old days, we used to make these things. It was a great fun experiment again. We did things so much more fun in the old days. What you would do is you would take this long tube and you would take a beaker of mercury and you pour it in there, fill it up. Mercury would of course spill and go everywhere, but you fill the thing all the way up. Then you put your thumb over the end of the tube, turn it upside down, and stick it in the jar of mercury, let go. The mercury drops, vacuum, until it balances the air pressure, and that's your column of mercury. Now, as we all know, mercury is now considered a bad neurotoxin, so you can't touch it, you can't even be in a room with it. So, can't do that anymore, but gosh, it was fun. When this height here is exactly 760 millimeters, that is referred to as atmospheric pressure. We will describe atmospheric pressure in terms of millimeters and another unit, and that's the atmosphere. 1 ATM, 1 atmosphere, is exactly equal to 760 millimeters of mercury. Same exact thing. Now sometimes, just to be confusing, books will, instead of using millimeters, they'll use the term torr, T-O-R-R. Torr, millimeter, same thing. As we said earlier, pounds per square inch, 14.7, but we don't use that in science. That's what you would use on the street. But 14.7, we're not going to use the English measurements, just millimeters and atmospheres. Any question? Magic number is 760. All right, let's get into our gas laws then. I have here a cylinder. This is a piston. If I push down on the piston, it'll compress this gas. And as it does, it will increase the collisions here. That increases the pressure, which is read on this little gauge. So this is a simple sealed piston cylinder. Okay? What we're going to talk about first is called Boyle's Law. Robert Boyle was a chemist a long time ago, and this is his law. Basically, he says the volume occupied by a fixed quantity of gas is inversely proportional to the pressure. What that means is, the bigger the pressure, the smaller the volume. It actually makes great sense. Let's go ahead and demonstrate this anyway. Here is our piston. First thing I'm going to do is put a very light weight on the top. It's going to be so light that it's really not going to compress the gas at all. Nothing happened. Very small force, really no change in pressure. But if I put a large mass on here, a large mass compresses the gas and the volume goes down. The greater the pressure, the smaller the volume. Now that makes sense, right? We can do this in a more defined way if we have our cylinder and we simply do a plot of the pressure we're applying and the volume that the cylinder occupies. As I start this little movie, this is going to compress, the volume will go down, so down this way, as the pressure goes up. The dependence looks something like this. Volume goes down, pressure goes up, and there's our curve. Now the first thing you note here is that it's nonlinear, isn't it? If you think about it, that makes sense. Because the gas here itself, the gas particles have a volume, don't they? And because of that, this can never drop to zero. Therefore, this must be asymptotic down here. As our pressure gets really high, we're still going to have some volume associated with it. So we wind up with a nonlinear dependence. Well, Boyle did this experiment, and he saw the same thing. If you make a plot of volume and pressure, it is nonlinear. However, Boyle sat there and looked at it and said, I remember my 8th grade math. That's a hyperbola. And if I have a hyperbola, I can convert that curve to a straight line simply by plotting volume here against 1 over the pressure. That's the equation for a hyperbola. So if we do that, volume versus 1 over pressure, we wind up with a really nice straight line. Okay. Everybody likes straight lines. Easy to predict from a straight line. The equation describing this basically is this. Volume is proportional to 1 over P. That's all we're saying. The little sign here, the little squiggle, that's the proportionality sign. Volume is proportional to 1 over P. That means it's a straight line. Now, a trick that we're going to do 2 or 3 times here today has to do with the proportionality sign. Mathematically, whenever you have 2 things that are proportional, you can change that to an equality. Put an equal sign, as long as you stick a constant of some sort in there. So this equation could also be written this way. Volume is equal to some constant, don't know what it is, don't care what it is, times 1 over P. Turns out that this constant is actually the slope of this line, but we don't care about that. Proportionality, all you do is stick in a constant, and you can do an equality. This is Boyle's law. Okay, let's take this and apply it to our 2 cylinders. This is what we just wrote, and I'm going to rearrange it just a bit. I'm going to put the P up here, so I have PV is equal to our constant. Simple math, everyone see that? All right, for any given sample of a gas, this tells us that pressure times volume is a constant. Okay? So, our 2 examples, the feather and the anvil, PV is a constant. Now this is the same gas in the same cylinder. So over here, P2V2 is still a constant. And in fact, because it's the same cylinder and the same gas, these 2 are exactly the same constant. So now think about it this way. If P1V1 is equal to a constant, and P2V2 is equal to the same constant, that means that P1V1 must equal P2V2. This is how you write Boyle's law. P1V1 equal to P2V2. Both equal to the same constant, so they must be equal to each other. All right, this is Boyle's law. Let's see how we can do a problem with Boyle's law. We have 12.5 liters of a gas. Our pressure is 0.82 atmosphere. So that's our 1 state, P1V1. We're going to change the pressure to 1.32 atmospheres. What is our final volume? Now right away we know We're starting at pressure of 0.8, we're going to 1.3. Pressure's increasing, the volume's going to decrease, right? We know that. We know what to expect. All we have to do is take Boyle's law and solve it for V2. That's what we're looking for, our final volume. So quickly take Boyle's law and solve it for V2. Just going to divide by P2. So P1, V1 divided by P2 is V2. There's Boyle's law. And now we've solved for V2. All right. All you need to do is go to your problem and pick out the terms. P1, well, that's 0.82, isn't it? V1 is 12.5. P2, 1.32. So we take and we plug them in. Now as we look at it, by gosh, we have atmospheres up top and atmospheres on the bottom. They're going to cancel, aren't they? So how do you solve the problem? You take your happy calculator and you just multiply 0.82 times 12.5, divide by 1.32, and you get 7.8. We started at 12.5. We increased our pressure, and the volume decreased. That is a Boyle's law calculation. Now what's important here, obviously, is that your units must all match. And we have liters and liters, atmospheres and atmospheres. If by some need, for some reason, somebody made one of these in terms of millimeters, what would you do? Well, you would remember 1 atmosphere is the same as 760, right? So you just have to convert one way or the other. It's a little bit of a bother, but you can do that. Go ahead and look at this one, and I'll hush for a moment. We're looking here for P2. Solve Boyle's law for P2. Substitute and do your calculation, or at least set it up. There is Boyle's law. We are given an initial volume and an initial pressure. We're changing our volume, we're decreasing our volume. We expect, because our volume goes down, the pressure must go up. We're solving here for P2, and it's simply going to be P1V1 over V2. P1 is 35 millimeters. V1 is 150 milliliters. V2 is 50 millimeters. Plug them in. Look at our equation, and we're very happy with ourselves because milliliters are going to cancel. Our calculation is simply 35 times 150 divided by 50. Our new pressure is 106 millimeters. Now, how many atmospheres would that be? If there's 760 in one atmosphere, you would just divide 106 by 760. Now, of course, there's a tutorial for this. These problems essentially require you to, of course, do Boyle's law calculation, but quite often you're going to have to do simple conversions. In this case, we have a volume in milliliters and a volume in liters. So that's easy because it's just 1,000 to 1, isn't it? All right, so here's our problem. We're looking for our resultant pressure. That's P2. Start off with Boyle's law. We are given V1, 5 atmospheres. That's this. V1 is 5,050 mils. That's this. We're looking for P2. V2 was originally given in liters. I'm going to change it to milliliters just by multiplying by 1,000. I just as easily could have divided this by 1,000 and made it 5 liters for V1. Doesn't matter how you do it. It always works. All right, Boyle's law. P1, V1, P2, V2. We want to solve this for P2. This is our equation. Simply plug in our numbers. Let's see, we're looking for this in atmospheres. The 4.54, rounding up to 3, and we got it right. So in a problem like this, just do a scorecard. What you got, convert if you have to, solve for the variable you want, plug it in, and the math is really simple. 5 times 5,000 divided by 5,600. Any questions? Go ahead and try to do this one. Initial pressure and volume. Pressure 2350 millimeters. Volume 8520 milliliters. Ooh, this is given in atmospheres, and we want the answer in liters. So we have to do 2 conversions, don't we? To convert millimeters to atmospheres, how would you do that? Divide by 760, the magic number. Divide by 760. To convert milliliters to liters, divide by 1,000. All right, here's our players. Our pressure was given as 2350 millimeters. What I did here for the P2 was I took 5.6, multiplied it by 760, so that I have milliliters. You can do it the other way. Again, it doesn't matter. They simply must be the same. Our volume. Since we're looking for liters, I converted V1 to liters just by dividing by 1,000. All right, we're looking for V2. So we write down P1, V1, P2, V2, and solve for V2. Plug in our numbers. Do our very simple math here. This is in milliliters. We want it in liters. So we simply divide by 1,000. We get 3.58 liters. Now once again, if you can do 5 of these guys, is important to you. If you didn't do tutorials last time, you gotta be kicking yourself by now. Do them this time. A Boyle's Law tutorial is worth 10 points. Only need 5 correct answers, 10 points for your next exam. Don't miss the opportunity. Yeah,
You don't have to do it twice, right? Just one time? You just got to do it once? and
just
you're
do
done?
it once. 5 correct answers, send it once. Put your real name in there, not an email address, so I can figure out who you are. 10 points on your next exam. All right. So much for pressure volume. There's also a pressure temperature, a volume temperature relationship. We will call this Charles's law. Now, Charles is his last name, not his first name. He's not a Charles. Charles is his last name. But this is the relationship between temperature and volume. Now, we're going to demonstrate this here by taking this balloon, this happy little balloon, and we're going to dump liquid nitrogen all over it. Liquid nitrogen is minus 196 degrees centigrade. Very cold. What it is going to do is cool the air in this balloon. Here's what happens. Or unsuspecting balloon. Here comes the liquid nitrogen. As the temperature decreases, the volume decreases. This ugly little wrinkle thing. Now it's starting to warm up. As it warms back up, the volume increases. What we've just described here is a simple linear relationship. Temperature goes down, volume goes down. Temperature goes up, volume goes up. This is Charles's law. Nice, simple, linear relationship between temperature and volume. Any questions? All right, balloons are fun to play with, but nothing beats a good plot, right? So what I'm going to do here is an experiment. I'm going to take a fixed quantity of gas. I'm going to start off with 0.25 moles of gas. And I'm going to change its temperature. And as I do that, I will record the volume. Here's my 0.25 moles. As I lower my temperature, by gosh, the volume decreases. Right? Now let's just make sure we didn't get lucky that time. Let's do it again with half a mole of gas. Same thing. Linear relationship, drop our temperature, the volume drops. 0.75 moles, same thing. All right, I'm convinced. Nice, simple, linear relationship. Temperature drops, the volume drops. Everyone agreed, we're good. Now look at these lines. These lines look like they're going somewhere, don't they? If we took these and extended them all the way down till they hit the axis, by gosh, they all hit the same point. How about that? Doesn't matter what gas you use. Doesn't matter how many moles you use. You extend these lines, they always hit exactly this same point. That's minus 273.15 degrees centigrade. This is the temperature that we refer to as absolute zero. It's the temperature at which a gas would have no volume. This is also defined as zero on what's called the Kelvin scale. Kelvin is the temperature scale you must use for gas law problems. Centigrade won't work, has to be Kelvin. Kelvin starts at absolute zero. Everyone's heard of absolute zero. Now you know where it came from, right? All right, so let's look at Charles's law. We know that temperature and volume are directly proportional. Lower the temperature, we lower the volume. If we have a gas in one state, we change its temperature, its volume is going to change. We can represent that like we did before. We say that volume is directly proportional to temperature. Take our proportionality sign and dump it. Put in the equal K. Okay? Now if we have a two-state system, that is a gas at one temperature, cool it, warm it, whatever, to the other. We're going to have two situations. Let's pull our constant out, and that's going to put V over T. For two different situations then, we could say V1 over T1 is equal to a constant, V2 over T2, same constant, so they're equal to each other. This is the expression right here. Make sure you write this down. This is Charles's law. V over T equals V over T. Now, like I said, the T here must be Kelvin. It doesn't work unless it's Kelvin. Centigrade. Water freezes at 0, boils at 100. Centigrade and Kelvin differ by the 273. Therefore, on the Kelvin scale, water freezes at 273 and boils at 373. Same number of degrees, but it just starts at a different point. Let's practice just a second converting between centigrade and Kelvin, because you need to be able to do this. It's simple because it only differs by the factor of 273. Go ahead and convert these guys from centigrade to Kelvin. Remember, here's our conversion. Centigrade plus 273 is Kelvin. Write that equation down. Centigrade plus 273 is Kelvin. All right, so all we have to do is add 273, don't we? So if we're at 1,000 centigrade, this is 1273 Kelvin. Now here we're at minus 150. We're still going to add a plus 273 to it, right? Minus 150 plus 273. We're at 123. Yep.
What is the big T and the little t mean again? The big T and then the little t?
The expression for Kelvin is uppercase T, and here it's lowercase t. But you don't need to know that. Just centigrade plus 273. That's what you need to remember. 100 degrees centigrade plus 273, 373, the boiling point of water. Oh, it's a very, very simple conversion. If we were given Kelvin, we would simply subtract 273, wouldn't we? All right, let's do a simple Charles's law problem. Here we have 50 mils. We're at 26 degrees centigrade. Right away, you know you've got to change that to Kelvin, right? First thing you say to yourself, oops, got to change that to Kelvin. Add 273 to it. Our final volume here is 62, and we're looking for the final temperature. Well, this is Charles's law. We know everything except T1. What was our end? I think that should be T2. So I think that should be T2 because there's a T1 there. Change that to 2 in your mind. All right, Charles's law looks like this. And we're solving for T2. Make sure you can do the simple math. Got to bring T2 up, bring T1 up, bring V2 down. V2, T1, V2, T1, divided by V1. T2 is out. All right, our volume number 2 here is going to be our 64. Volume 1, going to be 50. Our temperature, we must convert this to Kelvin. How do you do it? You add 273. So we're essentially 300 Kelvin. Take and plug all your numbers in. And we look at it. We have milliliters top and bottom, and they cancel. So to get the answer, we simply multiply 62 times 300, divide by 50. Easy to do on your calculator. We're at 373.8 Kelvin.
What did you multiply the 26.4 by?
That's this 62 times
Yeah,
300.
the top. How did you get to 99?
How did we get 299?
You have 270.
Remember, centigrade, we must change to Kelvin. We do that by adding 273 to our centigrade. Do our simple multiplication here. We have 373 Kelvin. Go ahead and give me that number in centigrade, the 3 significant figures. How do we do that? Just the opposite of what we did up here. We're going to subtract 273. 101 centigrade to 3 significant figures. Any questions? Now, if I did a tutorial for Boyle and I didn't do one for Charles, that would just be so unfair, right? Here we go. We have a temperature in centigrade. We want our answer in Kelvin. We have a volume in liters. We have a volume in milliliters. So we just have to do those very simple conversions. We can do those, right? Start off just by making our list. We have a volume and temperature. So this is V1, T1. Volume is 1100. Temperature is 106. Change this to Kelvin. Here's our V2. And we're looking for T2. Okay? What happened here? Well, okay, so here's our initial volume, 11,000. Here's T1. We add 273 to make it Kelvin. Right? Here's V2. Now I just decided to take this and make it milliliters. I could have done it the other way around. Doesn't matter, as long as they're the same. And we're looking, of course, for T2. Remember, we have V1 over T1 equal V2 over T2. That's what we have. We're solving here for T2. Practice this, make sure you can do the basic algebra. T2 is going to be V2 T1 divided by V1. All you do is reach up top, grab your numbers, stick them in. Here we go. And this is 264 Kelvin. Now once again, Charles's law calculations are a little more complicated than some of the other ones. So you get 5 of these right, send me your thing, 10 points on your next exam. Okay? Everyone got that? All right, we have one more thing we can do with this plot. We made a plot, you know, you may as well use it every way you can, right? It's a lot of work. What I want to do is sit at one temperature and see how the volume varies as we increase the number of moles. So let's just sit here at 473. I'm going to take these 3 mole values, these 3 volumes, and plot them. Clearly, as the number of moles increases, the volume increases. This is our mole-volume relationship, also called the Avogadro relationship. If we do this, holding temperature constant, and make a plot like this, it looks like this. As we increase the number of moles, the volume increases, and it's linear. This is Avogadro's law. Simple as it can be. More gas you have, the more moles you have, the bigger the volume. It even makes sense. All right, so we have 3 things here. Boyle's law tells us that volume is proportional to 1 over T. 1 over P. Okay, that's Boyle. Charles told us that volume was directly proportional to T. That's Charles. And Avogadro tells us volume is proportional to the number of moles. A little n we'll use for that. Now remember the trick that we did? We said if all of these things are proportional to the same thing, we can just combine them. If volume is proportional to 1 over p, t, and n, we can say it's proportional to 1 over p, n, and t. That makes sense, right? Now remember our trick with the proportionality sign. We can get rid of this if we put in a constant, correct? That's what we've done. Instead of calling it K, however, just for the heck of it, I'm going to call it R. And I'm going to say R represents the universal gas constant. Therefore, V would be this constant R times NT over P. All right, well that's good. That's right. That's correct. That makes sense. But I don't like that equation. So I'm going to rearrange this a little bit. I'm going to bring the P up from the bottom, put it here in front of the V, and I'm going to write it like this. PV equals nRT. It even has an internal rhyme to it. This is the universal ideal gas law. It contains the pressure, the volume, number of moles, and the temperature. This is the one equation that links it all together. And it even rhymes. PV equals nRT. You could say that as you fall asleep at night. PV equals nRT. Only problem is, what the heck is R? If we're ever going to solve anything, we need to know what R is, don't we? Turns out that we can figure this out very easily. This is what Avogadro did for us. He found that if you were at 0 degrees centigrade, or 273 Kelvin, if we were at 1 atmosphere, then 1 mole of a gas whatsoever, 1 mole of it, occupies 22.4 liters. Now that's amazing, but it's true. Doesn't matter what the gas is, if you're at 0 degrees centigrade, 1 atmosphere is 22.4 liters. All right, so let's take this and simply solve for R. PV over NT. We know all these numbers, let's plug them in. First thing we do is we look to see if we can cancel anything. And we can't. Oops. But okay. Do our math. 1 times 22.4 divided by 273 is the obnoxious number of 0.082057 with the obnoxious units of liter atmosphere per mole per Kelvin. I can never remember this either. So if you ever need it on an exam, I will give it to you. Okay? Don't worry about remembering it. It has these obnoxious units, and it's a funny number. But this is the value for R. All right, we know what R is. There's one more trick we can do. With PV equals nRT, if we know 3 of the things here, or 3 of the 4, any 3 of the 4, we can calculate the other one. So for any gas under any conditions, with PV equals nRT, if we know three things, we can calculate the fourth. That's nice. We can also rearrange it a little bit so that we can do our piston experiment. That is, change one thing or the other. And for this, we simply solve for R for state 1 and R for state 2. Again, if they're both equal to R, they must be equal to each other. So we have a single state and a two-state solution. Now, on your exam, we're not going to have to do things like I'm going to show you. But I just want to show you how it works, okay? On your exam, the calculations you do would be either very simple Boyle or Charles, and intuitive stuff. But let's go ahead and use these equations to do a more complex calculation, just to show you what you can do. For a single state problem, where we're just looking for a missing item, we use PV equals nRT. For a two-state problem, we use this guy. All right, let's look at a two-state problem. Lots of numbers, confusing as all get out. But we have 0.05 liters. Our pressure, 745. We're at 26 centigrade. We must change that to Kelvin. We raise our temperature to 404 Kelvin. Our volume, or our pressure, 106 atmospheres. What's our final volume? This is going to be our two-state system. The number of moles doesn't change, so we can just forget it. Just leave that out. We want to substitute in for all these guys. Our 26.4 to Kelvin is 300. On this side right here, we know everything except our final volume. That's here. 106 atmospheres, 404. Solve here for V2. Now we see we have atmospheres top and bottom, Kelvin top and bottom, and we're left only with liters. Do our math. That's not difficult math once you're at this point. 0.98 times 0.05 times 404 divided by 300 divided by 1.06. We're at 0.06 liters. So that's how you would do a combined problem. Now there are two more gas law problems tutorials. Again, you can get 10 points for each of these, but they're going to be much more complicated. But think of it as 40 points possible, right? If you do all 4 of the gas law tutorials. Let's just see how this works. Here we're given a pressure, a volume. Here we're given a pressure, a volume, and a temperature. We're looking for the initial temperature. Number of moles doesn't change, so you can ignore the end. Here's what we're looking at. Keeping score, P1, B1, looking for T1. We know P2, B2, and T2. I take my millimeters, convert it to atmospheres. How did I do that? Divide by 760, right? I rearrange in my equation. T1 is P1, V1, T2 divided by P2, V2. I substitute, and we're at 337 K. do one more. This is the PV equals nRT problem. So there are two, there's a combined gas law, and there's a PV equals nRT. Here, we have a system with 5.1 liters, 0.396 moles, and 291 Kelvin. All we're looking for here is the pressure. So we know everything except our pressure here. We know R, we know 8, whatever. Looking for pressure, no volume, no number, no temperature. We just take PV equals nRT, solve for P. That's nRT over V. Substitute 1.86 atmospheres, but just to be mean, the computer said I want to put this in millimeters. How do you convert this to millimeters? How do you convert it? Multiply by 760. 1.86 times 760, 1408 millimeters, and that is correct. Now the actual calculation here is 1408. I rounded it to 3 significant figures, 1410. I'll tell you a secret. When I wrote the little algorithm to do this, I built in slop for about 5% plus or minus. So if you put in 1408, you get it right. Frankly, if you put in 1450, you'd probably still get it right. So there's slop in all the answers here, just in case you calculate it off or round off just a little bit. Any questions? Let's do one more. Go ahead and do this one yourself. We're looking for a temperature in Kelvin. Here we have pressure, we have a volume, we have moles, and we're looking for temperature. Remember, R has units of liters. Remember, R requires liters. So whenever you do PV equals nRT, the volume must be liters. So we'll simply change this. 8,000 mils, 8.3 liters. Substitute in PV equals nRT, solving for T. PV over nR. So here's our PV. R is 0.0821. That's our number of moles. And we're at 225 Kelvin. Once again, 5 of these right, 10 points on your exam. Don't miss this opportunity. Speaking of exam, these are some questions straight off an old exam. Which of these properly states Boyle's law? remember, well, we go back and look half a dozen slides ago, Boyle's law we said was P1, V1, P2, V2, right? We also said PV was always a constant, called it a K. And if you take this equation and divide by P2 and V1, we get this. All of those are correct representations of Boyle's law. Can't forget Charles. Which of these accurately reflects Charles's law? Now, what was Charles's law? It was V over T equals V over T, right? So T1, V1, T2, V2, that's all right. TV wasn't a constant, T over V was a constant. If you multiply this out, this is V1, T1, V2, T2. This is Charles's law, and none of those are correct. I can virtually guarantee you that on this next exam, you will have a question that's either like 1 or 2. Now, of course, they'll all be different, but I can virtually guarantee that. All right, here's a simple Boyle's law calculation that you might see on an exam. Remember P1, V1, P2, V2. We have a volume of 450, pressure of 1 atmosphere. Our volume is now, pressure is now 5 atmospheres. What's the volume? So we're looking for V2. 450 times 1 divided by 5 is 90. Now that's simple, right? We can all do that. When you compare centigrade and Kelvin, which is true? 1 Kelvin represents a larger temperature change than 1 centigrade. Nope. Remember, they're exactly the same size. Centigrade and Kelvin are never equal. If centigrade plus 273 is Kelvin, can they ever be the same number? No. That's the one that's wrong, or that's the statement that's true. Only readings in Celsius can be converted directly to Fahrenheit. Well, that's stupid. And all and none. Here we're at 25 centigrade and 1 atmosphere. We have a volume. Can raise to 100. The same gas will occupy what? So this is a Charles's law, isn't it? V1, T1, V2 over T2. We're solving here for our volume, V2. Write our equation, substitute our numbers. What do we have to do? 25 plus 273, 100 plus 273, right? Yeah.
Is it 273.15 or just 273?
I'm sorry?
Because in the other slide it was 273.15 or just
Yep, don't worry about the 0.15. 273, 3 significant figures. So 373, 25 gives us 298 Kelvin. Kelvin cancels. 373 times 1.5 divided by 298 is 1.88. Simple, simple math. What's the mass of a gas? 18.6 liter container at 20 degrees if the pressure is so and so. How in the world can we do that? Remember, PV equals nRT gets us moles, doesn't it? Look at our periodic table. We can get molar mass. So we'll start with PV equals nRT. We're looking for the number of moles. We are given 2.35 atmospheres, 18.6 liters. We're at 20 degrees centigrade, so we have to add 273, and this is R. We have 1.81 moles of argon. Now, we look at our periodic table. What does 1 mole of argon weigh? I can't read it. Somebody tell me.
Where?
39.9, so roughly 40 grams in every mole. We have 1.8 moles. 1.8 times 39.95. We have 72 grams of argon. And finally, STP, standard temperature and pressure. Standard temperature and pressure, 0 degrees, 1 atmosphere, they're both standard. How many moles are in a 35-liter vessel? Think back to chapter 4. What is the volume of 1 mole of a gas? 1 mole of a gas. They all have exactly the same volume. 22.4 liters, right? Well, we have 35 liters. So it's going to be more than a mole. What would 1 mole occupy at STP? 22.4. We have 35. So simply 35 divided by 22.4 gives us the number of moles. 1.56 moles. Oops. The dreaded none of the above. All right. You will not see anything on an exam, calculation-wise, that is more intense than these 7 that we have just done. If you can make it through the tutorials, you get yourself 40 points on your next exam. Any questions? All right, thus endeth the gas laws.